My name is Professor Joseph Wunderlich. I'm Professor of Engineering, Architecture, and Computer Science. And this is a lecture, introductory lecture on machine intelligence. And so we want to begin with symbolic AI versus neural networks. Now, some of the naming has been changed to tier of deep learning, and that's referring to neural networks. Traditional symbolic AI, it still exists in many ways, in many places, but it's more of the historic beginning of things. So symbolic AI, what that is uses special forms of programming and establishes rules that leads to certain outcomes in an efficient way. So it's pruning the search space, it's implementing heuristics, has inference. It's code, and it's set a set of rules that are subject to usually the programmer's ideas or an expert that they consult for an expert system. I have a whole history that you can learn about that in other courses you can find online. Some of my historical discussions of things. Now, neural networks are different. They use a collection of neurons in layers now to collectively generalize solutions. You give them a training set and a set of criteria or set of stimulus and desired outputs, and then it learns them, and they may be conflicting within the set. There may be conflicting things where one set of stimuli wants one result, another set wants something completely different, and then the weights, the interconnection weights that magnify the signals through between the neurons, those weights are changed incrementally to settle on some solution to satisfy multiple constraints simultaneously. So let's start off with here an example. Suppose you have two parents deciding between getting a puppy or a kitten for their baby to play with. So we assign a binary variable to this decision, a 0 for a puppy and a 1 for a kitten. So we'll just start out with a non-machine intelligence case where the parents agree that if either one of them really wants a certain kitten, the spouse will yield to that desire. This would be like an OR gate, where the parents assign the variables x and y, would assign an outcome of 1 for a kitten. So mom and dad looks like this. So either one of them wants a kitten or both, then you get a kitten. Otherwise, you get a puppy. And the decision process without pruning search space would look something like this. X, y equals 0, 0, then you get a decision equals this. And so you understand that from any programming you've had of those cases. Now, the symbolic AI case is where the parents would have some degree of confidence in their choice. This is one way to do artificial intelligence, expert systems. You put confidence values. It's like probability theory, but it's a little different. So confidence is different than probability, and you can read about that in my machine intelligence lectures. But so what you have here is a confidence that if they're only 20% sure each about, and they both agree, then you get this kind of variable input, and then then you're getting a puppy with a certain degree of confidence. You have to calculate that, and I have a link there that you can follow that will in the PDF version of this, or the PowerPoint PPTX version. If you're watching it on YouTube or the MP4, well, you have to type it in, I guess. If you're just watching the MP4 on YouTube, I'll try to put a comment to the PDF of this file so you have a clickable link. So now let's look at neural network case. So using the same thoughts of the parents as in the non-machine intelligence case, you have mom and dad and x and y, and there's no confidence here. We're just starting off with the first case where you have binary decisions on the parent's part, and so the output's a binary decision also. And we're going to train now a neural network to do this. So here is a 2-to-1 neural network. That means 2 inputs, 2 hidden layer neurons, and an output. There's also biases on here. You typically just set the bias coming in as a 1 signal, but the weights will change, and the weights, these weights, you initialize them. They can be randomized. There is actually ways, there's mathematical theories to how to initialize the weights to be based on the problem to learn more quickly. So in essence, what we want to do is we want to have this machine, this network, learn this decision process, learn to satisfy all these constraints, exemplars 1, 2, 3, and 4 simultaneously. So all the weights need to be changed such that all of those are satisfied simultaneously. Now initially they won't, and so each time all 4 of those are presented to the network, that's called one epoch. You see that on the x value of the graph. One epoch. And so the way this works, the learning process works. You see steps down here. You initialize the inner neuron connection weights to randomize values, or you can do it in a deterministic way, but typically just randomize them. Feed the neural net. Number 2, feed the neural network 1 exemplar at a time, each time using the error between desired output and actual output to change connection weights between the neurons. So this is backpropagation, the standard backpropagation. You take this error signal that's coming out when you give it an exemplar, feed an exemplar, you have an output that comes out, an actual output. You compare that to the desired output. You make an error signal, the difference between the two, desired and actual. And then you take that error signal and you backpropagate it. So then you'll change the weights between the hidden layer and the output layer. And then you propagate the error signal back through those weights into the first layer, connection matrix of weights between the hidden layer and the input layer. And so you change them all by a little bit, depending on the learning rate. You want to take tiny little bitty steps, or otherwise your gradient descent learning won't work. You'll jump back and forth over the crack in the error surface that leads to your minimum that you're looking for in your optimization and your gradient descent learning. That's you need Calc 3 and multivariable chain rule. Typically, you can learn that Calc 2 too, but multivariable chain rule. Not just chain rule, but multivariable chain rule and partial derivatives and some mathematics. But we're not going to do that here. It's just introduction. So, so steps 3 here: repeat this, feeding the exemplars and changing the connection weights for all 4 examples. So repeat number 2 until the output error is within reasonable proximity. So you do this one neuron, one exemplar at a time, and then that's an epoch, and then you do it epoch over epoch over epoch. You just repeat. This is actually I probably should put a step in between 2 and 3 here. So you do all of 2 over and over and over and over again, and I guess it says that in 3 until you reach some kind of tolerance. So you're trying to get binary outputs out of this thing, but you can see it's not binary. It's actually analog values coming out of the thing. So you're somewhere between 0 and 1, and you want to accept as an output value. You'll accept something less than 0.1 as being 0, and something more than 0.9 as being a 1. If your stopping tolerance is set at 0.1, you can change the tolerance if you like. If you don't have any tolerance, these things are asymptotic, and you'll just waste a lot of time trying to drive it to some absolute, 0 or 1. And you may get there eventually, but I wouldn't waste the time. So typically, you threshold it, or you put a tolerance. So number 4, after learning is done, the neural network will react instantly to not only binary outputs, but variations of the input. So this is very important. Statement number 4 here. First of all, you don't have to go through the learning process once you've trained the thing. You just feed it something, and it should respond exactly the way you like. It will for the exemplars. And just one feed, you don't no epochs here. I guess you'd say it's one epoch, but it's not even. But there's no learning, so it's just like half an epoch, just to feed forward right through one. You feed it, and it's only one exemplar, so it's not even an epoch. You just one exemplar at a time. It's a fraction. It's a very, very small percentage of the time. Just reacts immediately in real time. And these things are used for serious. And you can imagine whenever you need to react in critical situations in nanosecond, you have the neural network. You'd even embedded in hardware with the weights fixed. And it's super fast. I mean, nanoseconds. But it's not nanoseconds, and you could spend. Initially, I spent days sometimes waiting for the simulations to learn on the old machines. Now everything's super fast. You use CUDA cores on graphics processors, and things are many orders of magnitude faster now. But still, it's still, relatively speaking, much faster on the feed forward than once it's learned. And additionally, in that statement number 4, which is a very important thing, the network will react to things other than the training set. I'll say that again. The network will react to things other than the way you've taught it. So if you feed it something that's not just binary, it's some fraction, then it'll still react in some kind of way. And that's what we're going to see in a minute here, and which in a way that's probably most likely correct or close to what you would want, what you would anticipate getting. So that's a very important thing. That the neural network can adapt, or it's just inherent in the way it behaves, is that it can guess what you mean if you give it something other than the inputs that it was expecting from the training set. So you see in neural network case number 2 here, using the same thoughts of the parents as in the symbolic AI case. So now we are feeding it something other than binary inputs, and it's still learning. I mean, it's still giving us results like we would expect. So because the fuzziness, the uncertainty of the parents isn't so extreme now. If you up you put in something that's like 0.5s in here, somewhere between 0 and 1. Well, that that or even higher, you're gonna get some the indecisiveness of the input. I mean, the thing can't learn if you have no idea what you want, and then the thing's not going to tell you anything. But it can adapt to the fuzziness, if you will, of the data. So now continuing this same example, if instead of case number 2, instead of randomizing weights in the beginning, we use the weights that we learned in case number 1 with just binary inputs and outputs, no fuzziness in the inputs, we see that then it learns much faster. Then case number 3 is just as I think we mentioned. If once it's learned, it will just respond to an exemplar almost instantaneously. Case number 4, the same thing, almost instantaneous response if you give it something that's not exactly the inputs, something a little fuzzier in just the feed forward suite. It doesn't need to learn anymore, it's just responding. Now, case number 5 is an odd case where it's not really odd. I mean, this happens all the time where the things that are being asked to be done, learned in the training set, and the exemplars are contradicting themselves a little bit. So if for this case of a picking a puppy, if for some reason the one parent wants a kitten, or only one of them wants it, then the other one just is oppositional and says I don't want it, and if they both agree, then that's not they're not going to get a kitten. So I might have misspoke here. If they both want to get, if either one of them wants to get a kitten, they get a kitten. If they both want one, then they end up getting a puppy, which so the logic's a little bit messed up here, but there's it's human behavior, so you don't want to try to make it work out too much. And the neural network's actually pretty good at reading into this, the intent, and trying to resolve something. So regardless, here you have this what's called an exclusive OR, and it's counterintuitive because to even have such a thing, if you think about the stimulus, if both are 0, we get a 0 coming out. If you just imagine these signals going in and a signal coming out, and then you have a 0, 1. Well, you're giving a little bit of juice, right? A little bit of 1, a little bit of this some value, number, magnitude. So you're going to get some magnitude coming out. If the other variable, if x is 1 and y is 0, then you get something coming out. But if you have both of them feeding in, you get a 0. Well, now that's not going to be easily solved with just a single neuron. That actually held up research in neural networks for a bunch of years when some renowned MIT researchers, Minsky and Perret, said you can't do these nonlinear separable problems with a single perceptron. So it took almost 16 years before Rummelhart came up with backpropagation and layered networks to solve this type of problem. So anyway, here you can see now that in the graph it took longer to learn, almost 1,400 epochs as compared to 200 to 600-ish in the other previous examples, because this is a nonlinearly separable problem. Now this case number 6 is a little bit more odd, where for some strange reason the parents only get a puppy if both of them plus the neighbor all either agree to get a puppy, or for some really odd reason all want a kitten. So, stretching the logic here a little bit, although you can imagine the part where if the neighbor doesn't want a dog and the dog's barking, you could factor that in somehow. But overall the logic's a little weird, but just allow it so we can get this problem defined. And in reality, there's all kinds of problems, real-world problems, that lead to this kind of data. So you have now 3 variables, input variables, mom, dad, and the neighbor. And so you have 2 to the 3 equals 8 exemplars when you have, how many permutations of 3 binary variables you have. You have n number of variables. You have 2 to the n permutations. So you have 8 different combinations. And so this is the data you're looking at here. So it's almost like a big giant exclusive OR if you think about it, where the first one and the last ones are the ones contradicting the most, the biggest contradictions between the number 1 and 8. How long does that take to learn? And so you see that up there, and over 1,000 epochs for that to learn. Now I'd like you to take some time and read through this, the steps of the algorithm development, 1 through 8, and then look at some code. So take your time to look at this. This was code I wrote originally not in Matlab in 1991 to just lead up to tweaking the neuron transfer function to allow parallel processing in hardware to make single chip neurocomputer. That was my master's thesis. And then a second processor made a whole different kind of theory with more of biological inspiration after that. So I made 2 neural processor designs in 91 and 93. So take a look at this, look through it. Most of you know how to program, so just look through. You look at this stopping tolerance, ask yourself how that works, and the learning rate. That's something that you'll learn about. You can read other lectures. You don't want that too big, or you're not going to, it's not going to learn. And then you'll see the weights being initialized and just random values here. And then the main code. Go down, take a look at it, see if you can figure out how these incremental changes are being made to the weights. And then the output plotting here at the end, so some metrics, and then the whole code section for the 331 bigger architecture. And that's all the same, except just scaled up a little bit. And so just look through that, make sure that all makes sense to you. And lastly, this larger scaled up one ending and outputting some metrics.